for the 2018 AP Stats free response. We got the exam in 1 week, so hopefully you've done these problems and you're here to just watch and get some suggestions, see how I think about them. Or if you were stuck, you're here to learn how to do them. So let's start. I've seen all these questions at some point, but not in years, so they're pretty fresh to me. Let's go. The manager of a grocery store selected a random sample of 11 customers to investigate the relationship between the number of customers in a checkout line and the time to finish checkout. As soon as the selected customer entered the end of the checkout line, data were collected on the number of customers in line who were in front of the selected customer and the time until the selected customer was finished with the checkout. The data are shown for the scatter plot. Got it. So we're looking at how many people are in front of you in line, which means like when this 0 here, that means there was nobody in line when they went up. Here, there were 3 people in line when they went up. They just got through very quickly because they must have been small orders. Okay, A. Identify and interpret, in context, the estimate of the intercept for the least square regression line. Identify. Okay, so identify, we got to get that from here. So what are we going to get from here? We're looking at these. So this is telling us our equation is 174.4 x plus 72.95. So y equals mx plus b, of course. This is our y-intercept. So the y-intercept is 72.95 in context seconds. This means it is predicted that if there is no line, it will take 72.95 seconds to check out. That's always the idea of the y-intercept. It's if the x variable is 0. That's the interpreting part to check out. And that's always what a y-intercept is, right? The y-intercept is when x equals 0. In this case, x is customers in line. So we're saying there are 0 customers in line. That's how long it'll take to get through. Okay. Identify and interpret, in context, the coefficient of determination, r squared. So let's see. They give you the r squared adjusted. We always just ignore that. So in this case, r squared is 0.733. 0.7333. So this is saying, and this is another fill in the blank sentence. You just say that 73.33% of the variation in time to check out is the variation in time to check out is determined by, or is caused by, we'll say, is caused by the y variable, the number of people in line. That's just a fill in the blank sentence. I have that on my study guide. So you fill in the y variable here, number of people in line. Fill in the x variable, time to check out. So the r squared value is the percent of variation of the x variable. I'll say of. That is caused by the y variable. That's how you go. Can you say it is determined by or it is caused by? The only way they'll accept. They could probably say determined by. Wait, but you can't say caused by because this is not an experiment? I still think you can say caused. I mean, there is one word I always use. We're going to check the answers in a second. We'll check the answers in a second and we'll see. I really think, I think you could say determined. I think you could say caused. I think both would be fine. Oh, and then this is easy. I already even circled the outlier of 3. So the point 3 comma roughly 100 is an outlier because it is far away from the best fit line. Line of best fit. I'm going to say best fit line. That should be fine too. Alright, let's look at the answers. So we'll see what they said. I'm sure there's lots and lots of different possibilities. They really just want like a percent, like caused by. I think they're happy with the caused by. I don't have the scoring guidelines over here though. Okay. So, I mean, they say is that the value indicates that percent of the variability in time it takes for customers to finish checkout, including time waiting in line, can be explained by. So that's the same thing as caused by, right? We'll look particularly. So correctly identifies 72.95 communicates the concept of a y-intercept in context that includes both time and 0 customers in line. Indicates that the value of the intercept is a prediction by using language such as predicted, estimated, or average. We definitely said predicted. I knew that. I knew that was important. All right, B. Correctly identifies 73.33%. Provides a correct, possibly generic interpretation of R squared, and interpretation includes context. So first, context. I definitely did context. Let's look at the notes. The percent variability that is attributed between y and x. The proportion in the dependent y variable that is explained by, that is accounted for, is associated with. Okay. Let's see the wrong ones. The percent variability in the predicted y values that is explained. Yeah, not the predicted y values. That is explained. That is explained. So they don't say anything about cause. I think it's totally fine to say cause. I think it's totally fine to say caused. Because like that's not, they're not even really talking about that problem. None of those that they would address that problem in the incorrect interpretations if caused was that bad. I really feel like explained by is the same word as caused. Right? Because explained is not correlated. Explained is caused. Well, not necessarily, I suppose. But I still think it's fine to say explained. Alright. We're not going to sit here and think any longer. Okay, number 2. An experimental science and environmental science teacher at a high school with a large population of students wanted to estimate the proportion of students at the school who regularly recycle plastic bottles. The teacher selected a random sample of students at the school to survey. Each selected student went into the teacher's office, one at a time, and was asked to respond yes or no to the following question. Do you regularly recycle plastic bottles? I remember this question. I've done this before. Based on their responses, a 95% confidence interval for the proportion of all students at the school who would respond yes to the question was calculated as 58% to 81%. How many students were in the sample selected by the environmental teacher? So we have to work backwards here. That's kind of tough. So we have to say, wow, we have a lot of work to do just for part A here. So first we have to find the middle. We have to find the actual mean that she found. So we need to find the middle of this confidence interval. So I'm going to average them. Divide by 2. Ah, beautiful. So the average, the middle, is 0.77, which means the margin of error was 0.116 on each side. 0.816 minus 0.7. Now we use the formula. How do you calculate the margin of error? Well, the margin of error is equal to the z-score, or z star, or whatever, critical value, which in this case for a 95% is 1.96, times the square root of the proportion you found, which we determined was 7, times 1 minus 0.7, over n, because we don't know what the sample size is. And now you see that this is the equation right here that we're going to have to solve. So numworks would just, of course, solve that for us. I think that would take too long. So we'll just divide. We'll square. We'll flip. And then we'll multiply by 0.7 times 0.3. That should be right. You can verify to make sure all of that was correct. That was just algebra. So we're doing 0.7 times 0.3 divided by 0.116 over 1.96 squared. And if that's a decent number, that's a beautiful number. That's a beautiful number. We get 59.95. I think that shows us pretty clearly. So we get roughly, that's roughly equal to 59.95. So we will conclude that she sampled 60 students. That was a good problem because that was just like math. I enjoyed that problem. Okay. Given the method used by the environmental science teacher to collect the responses, explain how bias might have been introduced and describe how the bias might affect the point estimate. Yeah, they said that this time. We always have to do that. We have to explain how it will affect the point estimate, meaning will it go up or will it go down? And often, either answer is acceptable. But let's see here. So what is happening here? The teacher selected a random sample of students. Each selected student went into the teacher's office and was asked to respond to that question. It doesn't say who asked the question, though. Into the teacher's office one at a time and was asked to respond. So they don't say the teacher asked it. But I remember that kind of being the whole part of the idea. And that's really the only reason there's bias, right? Because it's the environmental science teacher asking it. I'm kind of curious what other causes, what other sources of bias could there even be. So that's what we're going to say. So, like, it was in the teacher's office. And since she's an environmental teacher, I wish it said that she asked the questions. I mean, really, the whole thing is they're self-reporting. That's actually what it is. That's the bias. They're self-reporting. It's response bias. We can even name that. Students might lie and say they recycle when they don't. This would give an overestimate for the population proportion. I'll go ahead and throw in it is response bias. They don't say to name it. And we didn't have to last time we had a question like this, but we'll go ahead and name it. I mean, actually, if it's wrong, you do lose points for it, so you really probably shouldn't name it. But that's right, so we will name it. Part C. The statistics teacher at the high school was concerned about the potential bias in the survey. To obtain a potentially less biased estimate of the proportion, the statistics teacher used an alternative method for collecting students' responses. A random sample of 300 students was selected. Each student was given the following instructions on how to respond. In private, flip a fair coin. If heads, you must respond no, regardless of whether you regularly recycle. If tails, you respond truthfully. What is the expected number of students from the sample of 300 who would be required to respond no because the result was heads? Okay, so that's simple enough. We say half will. $300 times 0.5 is 150. Right, so the idea that they're going for here is that you'd feel more comfortable saying no because you know half the people are going to say no no matter what. So the results of the sample showed 213 out of 300 students responded no. Based on the results of the sample, give a point estimate for the proportion of all students at the high school who would respond yes to the question. Okay, so here's the idea. 213 responded no. But we're going to assume that 150 of those would have done it no matter what. So what we've really found here is that 63 out of 150% said no. We want who would respond yes, so that means we want 1 minus that. Right? So 213 said they don't recycle. We take away the 150 who had to say they don't recycle. That means there were 63 left that don't recycle. So we'll do 1 minus that proportion to get the proportion that do recycle. 58%. 0.58. A lot lower than the 0.7 she got before. Rough. Rough for her. For them, I should say. Okay. Use the standard error where P is between 0 and 1. Okay. Shows evidence that 0.7 was correctly used in the standard error. Used 1.96. Shows evidence that 0.116 was correctly used as the margin of error. Includes a single positive whole number answer. Right. And the answer was 60, right? Boom. Nice. We definitely got all of that. Definitely got all of that. And of course, you have to round it to a whole number because they're people. I didn't talk about that, but that is why I definitely right away rounded to 60. Okay. Explains why the responses to the survey might differ from the truth about students in recycling in context. For example, the survey was not anonymous. That's all I had to do. Okay. So I definitely did that. Explains how the response to the survey might differ from the truth. Well, how responses. Oh, I know. I said that. Students might lie and say they recycle when they don't, and then describe how this will affect it. It'll go up on the population proportion. Oh, overestimate for the population proportion. Yes, so it gives you a higher sample proportion, but an overestimate for the population proportion. Yes. Yes. Next. Essentially correct if the response gives an answer of 150 and gives an answer of 0.58. And that's it. There's no work even needed to be shown for that one. That's a beautiful thing. Man, we're making good time. 17 minutes in, 2 questions in. All right. Oh, I remember this one. I like this one. Number 3. Approximately 3.5% of all children born in a certain region are from multiple births. Of the children born in the region who are from multiple births, 22% are left-handed. Of the children born in a region who are from single births, 11% are left-handed. What is the probability that a randomly selected child born in the region is left-handed? So should we try to use formulas? Maybe I'll try to use formulas just for fun. Instead of, normally for something like this, I just set up a two-way table right away. But let's get some of these probability formulas. These two are the only ones we're going to need. All right. So what do they give us here? They give us some givens, right? Of the children who are from single births, that many are left-handed. So they tell us that the probability of the children who are from single births, single given left. No, it's left given single. Left given single. So that's going to be the probability of left and single out of the probability of single. So I guess that's kind of the problem, isn't it? All right. Let's draw a two-way table. Two-way tables, once we get the two-way table, then the question just becomes easy because we already know everything. So the two-way table is just the hard thing. So how do you set up a two-way table? Well, we're going to have our two different things that we care about, one across the top, one on the bottom. And every one of the categories, they have to add up to 100%. It has to include everybody. So we're going to have Actually, I'm going to do it on the outside. We're going to have single births. We're going to have multiple births. And then we're going to have right-handed or left-handed. They're definitely assuming that you're either left or right-handed. Okay. Wait, I still did this wrong. That goes there. Those goes there. The extra boxes are for the totals. So we're looking at the total. I'm going to do it in decimals. We're looking at the total being 1%. 100%, I mean. We know approximately 3.5% of all children are born from multiple births. So we go to multiple births. We go, this total is 0.035. We go, of the children born in the region who are from multiple births. I guess this is kind of the hard part. Of the children born in the region who are from multiple births, 22% are left-handed. Oh, no, because we know how many are in multiple births. So this is saying, of this, out of this 0.035, there's some amount that is left-handed out of that 0.035, and that gets us 22%. This is X, our X left-handed multiple births. So it says, of the children born in the region who are of multiple births, 22% are left-handed. So we're taking multiple births left-handers out of the total multiple births is 22%. Yes. Now we just have to solve. So 0.22 times 0.035 is a very small number, and that makes sense. So this is 0.0077. We'll go ahead and get the box above it by doing 0.35 minus that answer to get 0.035 minus that answer. 0.0273. Because you know the multiple births, they got to add up to the total, right? And then we're going to do probably like the exact same thing for single births. So they tell us that of the children who are born from single births, okay, well, first, how many are born from single births? If 3.5% are multiple births, that leaves 0.965 for single births. So now they're saying that the X left-handers, we'll go Y, I guess. Let's throw a little, should have kept that X. Let's throw X, let's throw Y, and then we're going to have Y out of that 0.965 will get us 11%. So that means Y is just 0.11 times that. 0.11 times 0.965. 0.1062. So then we'll do 0.965 minus that answer to get the top box. And now that we have every single box in here, those don't totally add up, but that's okay. Well, we don't have those totals. Should we do that? Do that plus 0.0273. It's 0.8862. And then do 1 minus that answer to get 0.1139. All right. Now that we got the two-way table, it should all just be easy. A, what is the probability that a randomly selected child born in the region is left-handed? We've got that right there. 0.1139. What is the probability that a randomly selected child born in the region is a child from a multiple birth, given that the child is left-handed? From multiple birth, out of 0.035, no. Given that the child is left-handed. It's out of left-handers. It's out of this 0.1139. But what do we want? We want multiple births. 0.0077 out of all of that. 0.0077 out of 0.1139. Boom. About 6%. 0.0676 from multiple births is left-handed. What is the probability that a randomly selected child born in the region from a multiple birth, given that the child is left-handed. Okay. A random sample of 20 children from the region will be selected. What is the probability that the sample will have at least 3 children who are left-handed? At least 3 children who are left-handed. So we don't want only 2 children, or 1 children, or 0 children. Or should we just do binomial? Maybe we'll just set up the binomial, because that's definitely quicker here. So we'll say that it's binomial because it's binary. They're independent. Why are they independent? I mean, we could say there's more than 200 children. I guess that still applies here, right? And this is all just so I can use binomial CDF. Fixed number of trials. N equals 20. Yeah, okay. And then we'll say we'll do binomial CDF. We want at least 3. So we're going to do from 3 to 20. Lower, upper. We're going to do N of 20. And we're going to do a probability of success is what? Lefties. And we're just sampling everybody. So 0.1139. Okay. And then we should just have to put that into the calculator. And that'll be nice and easy to do because we have numworks. So we'll go to distributions. We'll go back. We'll go to binomial. We'll go to N equals 20. We'll go to probability of success is 0.1139. And then they'll show us the distribution. And then we'll say we actually want the big side in this case. And we want it to be bigger than 3. And that's actually a pretty good percent. 0.4024. All right. And that's everything there. So try to make a point to go faster. So let's check our answers. Doing the two-way table really should show everything. And work is shown that includes correct numerical values using a formula and end results from a tree diagram or some other appropriate strategy. Yeah, I mean, I really just think I got, like, I made a two-way table. So I guess I didn't show any of my work for the two-way table, but it's because they add together. I think that should be fine. Did I calculate the probability correctly at least? Yes, 0.11385. I just used 39. Yes, that's all correct. 0.0676, that's all correct. 0.402, that's correct. All right, we got all the correct answers. For a problem like that, that means we did everything correctly. All right, I'm happy with that. On to number 4. Halfway there in less than 30 minutes. Dang, we're doing good. The anterior cruciate ligament, the ACL, of course, is one of the ligaments that helps stabilize the knee. Surgery is often recommended if the ACL is completely torn, and recovery time for the surgery can be lengthy. A medical center developed a new surgical procedure designed to reduce the average recovery time from the surgery. To test the effectiveness of the new procedure, a study was conducted in which 210 patients needing surgery to repair a torn ACL were randomly assigned to receive either the standard procedure or the new procedure. Based on the design of the study, would a statistically significant result allow to make a conclusion that the new procedure causes a reduction in recovery time compared to the standard procedure for patients similar to those in the study? Yeah, right? A medical center developed a new surgical procedure designed which conducted 210 patients needing surgery to repair a torn ACL were randomly assigned to receive either the standard procedure or the new procedure. Yes. Yeah. So I just do the conditions here. We go 1, it's random. 2, independent, because more than 2,100 people need surgery. I'm even throwing context in there. Look at that. And then normal, So 210 is greater than 30. So yeah, it meets all the conditions. And that's really it, right? So yes. Okay. B. Summary statistics on the recovery times from the surgery are shown in the table. Do the data provide convincing statistical evidence that those who receive the procedure will have less recovery time for those on average? Okay, so we've got to do a t-test. We got to do a 2-sample t-test. So we already did the conditions. It's a 2-sample t-test where we're going to say that mean standard is the mean recovery time for the new procedure. No, the standard procedure. And this is the mean recovery time for the new procedure. We got to make sure we don't allude to it being the sample. The way we said it makes it sound like it's the whole population, and that's what we want. So now we can set up our nulls. Our null is that the mean minus the mean new, we're going to say, I guess it doesn't matter, the mean new minus the mean standard is equal to 0. And then the alternative is we need the same thing here, and we need to make sure we're going the right direction. So let's reread it. Do they want a difference, or do they want one to be more than the other? Do the data provide convincing statistical evidence that those who receive new procedure will have less recovery time from the surgery on average? Okay, so we want this to be less than 0 then, actually. Okay, let's rejig that then. So we want the standard time to be longer. We're not looking, but right in this case, smaller is better. One of the rare cases that smaller is better. Okay, so now we got it set up. So the null hypothesis is that the recovery time of the standard procedure minus the new procedure is 0, because they're the same. The alternative is that the standard minus the new is bigger, because the standard takes longer. Okay, now we've got it set up. And what we're going to do too, we're going to calculate our z-score, because, well, no, that's for the confidence interval. We needed to calculate the z-score, I guess. No, we do calculate the z-score of our data. That was the problem we did. And then we can't pool it this time, right? That's what we tried to do last time. But actually, we can even look at the formula sheet, and we can see that, see, this is the special case where you're supposed to pool. Oh, there's a special case here too? I didn't remember that. Oh, because this is a new formula sheet, right? I don't think they don't have you do that anymore. They really don't care about that. I really think they don't care about that. We saw that on one test yesterday. So we're not going to pool them. So what are we going to do here then? We're going to do the mean, or mean hat, or yeah, I just don't understand the symbols I'm supposed to use. Like, the mean that minus that is 217 minus 86, so 31. And then the standard error is the square root of, we were just there, up here. This one, standard deviation squared over n. Right. I was just figuring out that I forget the square things. No. That's right. I was thinking with my question yesterday, but no, we're right. So standard deviation squared, 34 squared over the sample size plus 29 squared over the sample size. That's our standard error, or standard deviation, really. So the square root of 34 squared divided by 110 plus 29 squared divided by 100 is roughly 4.35. You expect it to be bigger than both of those. Wow, it's very much not. Wait. Or do you not? No, because when you're combining them... No, right. You expect it to be higher than like if you were just using one of them. But you'd expect it to be lower in general because it's not the standard deviation of the sample. We're looking at the standard deviation of the sampling distribution now. So yeah, so that's fair. That's correct enough. No, that's correct. And then so now, what do we need to do? We need to do 31 divided by that so we can find the z-score. So we say z star, I think you're supposed to do, is 31 over this 4.35, which is approximately 31 divided by the answer, is 7.12. Whoa. 7.12. I guess it's a lot. Yeah, it's a lot shorter. 7.12. The z-star is massive. So now let's go ahead and finish out by calculating the p-value. So we'll go back to distributions, back to normal. Type in, we'll just use the z-score. So we'll go mean 0, standard deviation 1, and we'll just pop in the z-score. And we want to know what's the probability that it's that or longer. So we want the other side of it. And it's very small. Oh, I didn't put this in, 7.12. It's very small. Yeah. So then P equals norm CDF of 7.12, comma infinity, comma 0, comma 1, label lower. You do have to label. Don't forget to label upper, mean, standard deviation. And it's approximately 0. So now we conclude. We say because our p-value is approximately 0, they don't give us... Do we have to set a significance level? Let's set a significance level up here just in case. Use sig level. Because you do have to do that first, right? You can't like calculate your value and then choose a significance level. Because our v value is approximately 0, which is less than our sig level of 0.05, we reject the null. There is evidence that the new procedure provides quicker recovery times. Very good. Very good. Very good. All right. Let's check our answers, although I'm pretty convinced I got everything right here. What do we need to see? This is question 4. Part A. Yes, it would be reasonable. Okay, very nice. Very nice. And then they calculated the same. Yeah, they got 713. I got a little different. Oh, I didn't do a t-test. I didn't do a t-test. I did a z-test. Oh. How do you do a t-test? I don't even remember how you do degree of freedom. It's the lesser one, right? It's like 99? Or is it the greater one? It's 109? How do you do the degree of freedom for a pair? It's a formula you have to use. Step 1, identify procedure. Purpose is 2-sample t-test. So I did all this. I did the conditions up here. So I just didn't do that again. Test statistic is 713. The p-value is the area greater than that. How do you get the degree of freedom? Is that a formula? I thought it was just -1. It's -1 if it's just a 1 sample. How do you do it for a 2 sample? Did they say what the degree of freedom was? I mean, so what did I actually score? Parameters are so section 1 correctly states that it's reasonable to make a causal conclusion, justifies the causal conclusion based on a random assignment of patients. Yeah, and I included context. Wow, that was even something I had to do. Very nice. Okay, parameters are defined correctly. I did. Hypothesis, I did. Correct test is identified. I identified that correctly. Correct test statistic for a difference of means is calculated. If standard symbols used with the appropriate labels, component 1 is satisfied. Okay, wow, I didn't even actually need to do that. If the correct test statistic is identified, but the response states an incorrect formula or uses incorrect notation, component 3 is not satisfied. Yeah, so I did not satisfy component 3. Wait. Or 4? The correct test is identified, but the response states an incorrect formula or uses incorrect notation. Component 3 is not satisfied. Correct test is identified by name or formula. Ugh. And I use the name t-test too, right? I did. Makes reference to approximately correct p-value that is consistent with the test statistic and alternative hypothesis. So I think I got all of it, but just that but those two parts. But how do you get the degree of freedom for a 2 sample? Is it that there's 2 ways to do it? I kind of remember that. And you subtract 1 from both of them and add them together? That's definitely not what they did. They used some formula. But it's roughly 208 is what they use for the degree of freedom. Yeah. Okay, so yeah, you got to use the degree of freedom. You can't use the normal distribution. So what we really needed to do was come in and do students t-test, degree of freedom, not that, but 208. Forbidden value? What? How is 208 specifically a forbidden value? Anything bigger than 200 is a... What? X is less than A. I mean, we wanted greater than A, but we could just use negative. Maybe I don't even remember how to do a t-test. -7. 208. Okay, so it did that time. That's like the same value they got? Well, it's not going to be the exact same value they got. Because they used a crazy degree of freedom of... They did 0.13, and they did a degree of freedom because they used some formula of 207.18. And then you get still not exactly what they got, but closer, I guess. They might have used an exact value for 7.13. But yeah, we've just totally forgot to do a t-test. That's crazy. We just totally forgot to do a t-test. Alright. We got 2 more. X bar for sample statistic mean. Instead of mean bar. Or mean hat. Mean hat works though too, right? I hate all the notation. Alright, we're going on to number 5. The following histograms summarize the teaching year for the teachers at 2 high schools, A and B. Teaching year is recorded as an integer. The first year teacher is recorded as 1, second as so on. Both data sets have a mean of 8.2 with data recorded from 200 teachers and 221. The median teaching year for one high school is 6. The median teaching year for the other high school is 7. Identify which one has which median and justify your answer. So... I mean, we can really just kind of calculate it, right? Or no, we can't. We have to look more at the tails. I mean, 6 and 7. So I guess, okay, so how many are these together? This is almost 80 and almost 35. So that's almost 115. And that would pretty much get you to the 7, right? Whereas here, these together are like 45 plus 45. So that's like 90 together. Whereas high school A had 200 teachers. High school B had 221 teachers. Oh, so it's kind of actually the opposite. Because over here, the median is the 1/10. Okay. So that's what it's going to be. So identify which school. B has a median of 6, which is the opposite of what I thought at first. B has a median of 6. There are 221 points, 221 teachers. There are 221 teachers. The median is the 110th. And there are about I mean, is it more than 110? So if we round down, it's 30. Yeah, it's more than 110. There's more than 110. 110 teachers with less than 7 years. That should be fine enough. That should be fine enough. Okay. An additional 18 teachers were not included from the data recorded from the 200 years teachers. The 200 high school. The mean teaching year of the 18 teachers is 2.5. What is the mean teaching year for all 218 students at high school A? Okay, cool. Just a nice little math question. So we go, the mean is 8.2. So I'm just going to find the total number of years. I'm just going to do 200 plus 8.2 to get the total number of years from those 200 teachers. And then I'm going to add on these 18 teachers that only have 2.5 years experience, or a mean of 2.5. And then that's going to give me my new total teaching years. And then I'm going to divide that by the new total number of teachers, 218. So you could use proportions, but it's all the same math basically anyway. So we're going to do, this is times, 200 times. 200 times 8.2 plus 18 times 2.5. So that's the total number of teaching year experience. And we divide that by 218. 7.7 years. Lovely. Lovely. All right. The standard deviation of the teaching years for the 221 teachers is 7.2. If one teacher is selected at random, what is the probability that the teaching year for the selected teacher will be within one standard deviation of the mean of 8.2? Well, it's not normal. So that's not what we want to do. We want to say the standard deviation is 7.2. What is the probability that the teaching year for the one selected teacher will be within one standard deviation of 8.2? So what is one standard deviation of 8.2? Well, if the standard deviation is 7.2, that means we're looking between 1 and 14.4. No, 15.4. So then we want to say from high school B, we just want to count how many teachers are between 1 and 15.4. Or between 1 and 16, I suppose. We just kind of have to do that. And I suppose we're all estimating anyway. Well, we're actually just going to be subtracting. So we're going to say 211, 221 minus all of these that have more than 15.4. So here and on. So we've got to go, we just got to estimate these. So it's going to be like minus 12, minus 8, minus 3, minus 4, minus 2, minus 3. And that'll be how many people? Oh, right. And 1 is everybody. Nobody has 0 years experience. So, yeah. That'll get us how many people that is. We don't need a calculator for that probably. So this is 20, 27, 32. So take away 30. Whatever. 221 minus 32. 189. 189 teachers have between 1 and 15.4 years. So 189 out of 221. 189 out of 221 is approximately 85.5% chance. All right. Think we did everything there, right? Let's check the answers to be sure. A. Oh my gosh. States that the median is 6 for B. Yep. And the median is 7 for A. Provides a reasonable explanation how the decision was made. Provides the definition of median or explicitly applies the definition. Yeah, I did that. I did that. Or you could also talk about skew, which I was trying to think about, but then I just ended up calculating it, and that was fine. Correct answer, the mean is 7.73. That's fine. Enough work to show the answer is attained by a weighted average. Yes, I did that. Calculates the approximate interval of 1 to 15.4. Correctly sums up 85.52. Yeah. Computes the probability using 221 as the denominator. Yeah. I did all of that. All right. Now, on to the dastardly question 6. We're actually 10 minutes ahead of schedule. We're supposed to spend an hour 5 on the first bit and 25 on this one. We're looking good. All right. Number 6. Systolic blood pressure is the amount of pressure that blood exerts on the blood vessels while the heart is pumping. The mean systolic blood pressure for people in the United States is reported to be 122, a standard deviation of 15. The wellness department of a large corporation is investigating whether the mean systolic blood pressure of its employees is greater than the reported national mean. A random sample of 100 employees will be selected. The systolic blood pressure of each employee in the sample will be measured, and the sample mean will be calculated. Let mean mu represent the mean systolic blood pressure of all employees of the corporation. Consider the following hypothesis. Describe a type 2 error. All right. Boy cried wolf. At the beginning, the villagers say, oh no, there's a wolf, there's news, when there is no news. But at the end, in the second scenario, there is news, but they don't think there is. So they would say, in the context of the hypothesis test, the test determines there is not evidence the blood pressure is higher than 222. The blood pressure is higher than 122. But it actually is higher. Yeah, that's the idea of a type 2 error. Assume the standard deviation of the systolic blood pressure of all employees of the corporation is 15. If mu is 122, the sampling distribution of X for sample size is 100 is approximately normal with a mean of 122 and a standard deviation of 1.5. That's just a formula, 15 divided by the square root of n. What value of the sample mean would represent sufficient evidence to reject the null hypothesis at the significance level of 0.05? Okay, what values of the sample mean would represent sufficient evidence at 0.05? Okay, so we want, for B here, it's like we want to draw out a normal curve. We want to say our average is here at 122. We want to calculate where this would be in order for this area to be 0.05. So that's easy enough. We're just doing a norm inverse of 0.05. Well, no. Well, we're going to do upper. Or can I just say left side? I was going to say left side. That is an input to my function. We're doing the left side. And we're doing with a mean of 122. And we're doing with a standard deviation of 1.5. And we're just going to pop that into our formula. So, well, not our formula. We're going to go to our distribution. So here, boom, normal. You know, the same place you do it the normal way. So 122, standard deviation of 1.5. That's a very small standard deviation compared to how high the blood pressure is. And then we want to know what is the area that is 0.05. Now, like I said, on the upper side, the right side. The right side, 0.05. Boom. 124 is approximately 124.47. Lovely. Lovely, lovely. Do we need to really do anything more? We shouldn't have to. The actual mean systolic blood pressure for all employees of the corporation is 125, not the hypothesis value of 122, and the standard deviation is 15. Using the actual mean of 125 and the results from part B, determine the probability that the null hypothesis will be rejected. Determine the probability that the null hypothesis will be rejected. Okay, so this is the weird thinky bits that we have to do. Let me actually add a page. So, C. So we're saying the actual is 125 and 15. Oh, that's easy enough. Yeah. So we say this is the actual. We got to put it on the actual now. We still got the standard deviation of 15. And we got to say what's the probability of getting a blood pressure that's... What do we want? Determine the probability that the null hypothesis will be rejected. So we want to know what's the probability of getting 124 or higher. Of 124.47 or higher. I don't really need to show too much work here. So we're saying we got a different mean, we got a different standard deviation, and then we're going to come in and we want the top half, and we want it to start at 124.47. And that should be a little more than half, 0.51. So we're going to go norm CDF from 124.47. That's our lower, to infinity. That's our upper, with a mean. Oh, come on. I'm trying to go too fast here. With a mean of 125 and a standard deviation of 15. And that is approximately 0.514. Okay. Yeah. What statistical term is used for the probability found in part C? Right, so what is this? I mean, it's probably a type 1 error, right? It's the probability of... Or no, it's the power. What is the power? The probability... Right, the power is the probability of rejecting the null hypothesis when the null hypothesis is false. So D, it's the power. There's really not much to talk about. It's just the power. I'll say it's the probability of rejecting given false. Okay. E. Suppose the size of the sample of employees to be selected is greater than 100. Would the probability of rejecting the null hypothesis be greater than or less than or equal to the probability calculated in part C? Okay. E. Rejecting. It'll be higher. Can we just say a higher sample size raises the power? It will be higher. A higher sample size raises the power. Sample size means higher power. Because the standard deviation is smaller. Or the standard deviation of the sampling distribution. Don't abbreviate that. Otherwise it could be like its sample distribution. Is smaller. All right. We dropped the pencil. Boy, that was loud. I apologize. And that's got to be it. So let's check the answers. But I really think I covered everything there. So, part A, a type 2 error occurs. Yeah. Part A includes a description of a type 2 error, the fact that alternative hypothesis is true, either generically or in context of the situation. There is not evidence the blood pressure is... Wait. But it is actually higher. Which is the alternative hypothesis is true. So I did say that. Part A includes the description of type 2 error, the fact that the null hypothesis is not rejected. There is not evidence the blood pressure is higher. Yes. Includes a correct z-score for the upper 5 percentile. Did I fall into that trap again? I didn't actually calculate the z-score. I really feel like you shouldn't have to calculate the z-score, actually. Because I calculated the probability. I didn't need to calculate the z-score. Recognize the null hypothesis will be when it's greater. Wait, what? Section 2. What is section 2? Part C. Oh. Just part C. Recognize the null hypothesis will be rejected when x is greater than 124. Provides the correct sampling distribution when the true mean is 125. Provides evidence of using the normal curve. And finds the correct probability. Was it 0.514? No. Oh, the standard deviation is still 1.5. Oh no. The standard deviation is still 1.5 because we're still talking about sampling distributions. Oh no. Okay. So that's my problem. So that should have actually been 0.64. Ugh. Yuck. That's a little bit wrong. D is just power. Yeah. The probability of rejecting the null hypothesis will be higher. Yeah. It'll be higher. Higher sample size means a higher power. Let's just read what they have to say down here. The name is the power is the name. Correctly states the probability would be greater. Correctly implies the standard deviation decreases. Ooh, I very specifically said that. Indicates the minimum value for which the null hypothesis is rejected decreases. Indicates that the minimum value for which the null hypothesis is rejected decreases. I should have said that. So, yeah. I should have said that, but I might have got points. It'll be higher. A higher sample means a higher power. I mean, that right there should have gotten it. I just had to be a little more specific because the standard deviation of the sampling distribution is smaller, making the min value to reject the hypothesis smaller. All right. Not bad. Not bad. That was definitely 5 material. What was it? It was like 4 E's and 2 P's at the end of the day. Or probably 4 4's and 2 3's at the end of the day. That's 5 material if I've ever seen it. But now that you've seen me mess up, you can come out here and get straight 4's.